Hello, today we are diving into some important and fascinating topics in mathematics and set theory, which is called cardinality. It is a concept that allows us to measure the size of the set not just for the finite set, but also for infinite ones. Uh, so this video will explore the basic cardinality comparing finite and infinite sets by discussing why understanding cardinality is essential in mathematics and beyond. Let's start with the basics. Cardinality measures the size of the set, essentially how many elements it contains. For example, if we have a set of 3 apples, we can say the cardinality of this set is 3. Simple enough. But we move beyond the finite sets to infinite sets. Things become more complex here. How do we measure the size of the infinity? Cardinality gives us the systemic ways to compare finite and infinite sets. We denote it using the notation, the absolute value symbols of a letter A. So the cardinality of a set A is read as a size of A. Understanding the cardinality isn't just abstract exercise. Finite sets are with specific, countable numbers of elements. For example, the set labeled A containing the elements 1, 2, and 3 has a size of 3. We write this as the absolute value of A equals to 3. Similarly, the set labeled B, containing the element apple and banana, has a size of 2. This is written as an absolute value of B equals to 2. Finite sets obey some basic properties. For instance, the empty set often denotes as a 0 with slashes through, has no elements, therefore its cardinality will be 0. Another key property is that for any subset labeled B, which is a part of set A, the size of B is always less or equal to the size of A. Finite sets are crucial in counting problems and combinatoric. For example, if you're arranging a groups of students in a line, you're dealing with the cardinality of subset and permutation. This concept also forms the foundational for probability. When calculating the likelihood of rolling a 6 on a die, you're working on a finite set of 6 possible outcomes. Now let's move on to the infinite sets. Unlike a finite set, infinite sets cannot be fully counted in a traditional sense. Infinite sets come in two main types, countably infinite and uncountably infinite. Countably infinite sets, such as natural numbers, can be paired one-to-one with the natural numbers themselves. For example, if you list the integers as 0, 1, -1, 2, -2, and so on, we can assign each of the natural numbers, assigns 1 to 0, 2 to 1, 3 to -1, 4 to 2, and so on. Uncountably finite sets, such as real numbers, cannot be matched in this way. Their cardinality is fundamentally large. To visualize this mapping in more details, let's consider the sequences. The natural numbers are listed as 1, 2, 3, 4, 5, and so on. The integers are arranged as 0, +1, -1, +2, -2, and so on. Notice how each natural number alternates between positive and negative integers, wrapping symmetrically around 0. This symmetric pairing is what makes the integers countable. It allows us to list all integers in the sequences, even though they extend infinitely in both directions. One key takeaway here is that any set we enumerate in the manner is countable, regardless of how large it might seem. This is a practice question for today. Pause the video, take your time, solve it, and come back to the video again. This was an easy question. The answer would be countably infinite. This is because the set A containing all natural numbers which can be enumerated systemically. Define a one-to-one correspondence between A and n, which is a natural number. Uh, for here, we can use Fn equals 2n, where n is a natural number. So therefore, if n equals to 1, then F1 would equal to 2. If n equals to 2, then F2 would equals to 4. If n equals to 3, then F3 would equals to 6, and so on. Since every element of A corresponds uniquely to the elements of natural number, A is countably infinite. Our second step here uh, is also countably infinite. This is because the set B containing reciprocals of all natural numbers, which can be also used for enumerating systemically. Define one-to-one correspondence between b and natural number, where fn would equal to 1 over n, where n is a natural number. For example, if n equals to 1, f1 would equals to 1. If n equals to 2, then f2 would equals to 1 over 2. If n equals to 3, then f3 would equals to 1 over 3, and so on. Since every element of b corresponds to uniquely to the element of natural number, b is countably infinite. For step 3, this would be uncountable. The real number between 0 and 1 cannot be enumerated systemically because they include infinitely many decimal expansions such as 0.1, 0.01, and 0.001, and so on.